The TVs are just not working. Go. Okay. Open input list. This is called RCA. It's a ripple carrier adder because carry outs from the previous adder is being fed into the succeeding adders as a carry in. Ripple carrier adder. And last time we are trying to create a subtractor out of it. So we need a XOR gate for each FA. B2, B1, B0. And here's a control bit. I'm going to short the control bit to C minus 1. Okay, so that's a basic structure of that ripple carrier adder and a subtractor. Right? So whenever the control bit is 1 or 0, it's a subtractor. That's a question. So do you need a 1 or 0 to enable that subtractor function to make it into a subtractor? You don't have to go through the XOR's logic every time, right? You just think about whenever you need a subtractor, you have to flip it and add 1 to it. So whenever you want to add 1 to this C minus 1, you need a 1 here. So you do need a 1 or 0 to enable that subtractor. So whenever you need to get a 2's complement of the B's, right? You need to flip it and add 1. So you are doing subtraction instead of addition. So you need a 1 here because it's being shorted to here as well. So you want to feed a 1 to all the inputs of the XOR gates, and at the same time, it's feeding a 1 to C minus 1 as well, right? So to enable the subtractor, so you need a 1 here to enable the subtractor instead of 0. And if you like, you can still go through the logic for XOR gates, right? You can think about, hey, if I put a 1 here, then 1 XOR B0 will be what? One XOR B0 is what? What is this? It's frozen. If B0 is 0, you're getting a 1. If B0 is 1, you're getting a 0. This is always inverting B0. So whenever you feed a 1 to this input of the XOR gate, it's inverting B0 and add a 1 to here. So exactly doing the 2's complement operation, right? So that's the first method to implement a adder subtractor using all these logic gates. And you can also use muxes. Still I-phase. The I-phase can be slow I-phase, can be fast I-phase. We're going to talk about pretty soon, which saves you a lot of space. So I can replace this XOR gates by using muxes. What's the motivation of that? Why do I want to replace it with muxes? You'll see pretty soon. These are smaller. A mux selects either input and transfer it to the output, right? Depends on the control bit. So here is B, this signal is B, and that's B naught. All these ones are B naughts. And this is the control bit, which is a selection bit. Let's put S here. There are two inputs being fed into the muxes. So if I give a 1, then I can select all the B naughts as a output to the output of the mux. If I give a 0 to S, it's going to pick up all these ones, all the B's. That's a function of the mux, right? And let me know what else I need to connect in this circuit. So I don't have this, right? Do I want to invert S or directly short S to here? Depends on how do you want to design, right? Since these two inputs are equivalent, not equivalent, these are, you can change the exchangeable, right? So there are two inputs. You can give this, assign this one to B naught and this one to B, or this one as B, this one as B naught, doesn't matter. Right? Depends on the circuit. If you do not have to invert S, if you can directly short S to here, which is the best, since you are saving space, you're not adding an extra inverter to there. So in this case, if I have S equals to 1, do I want to pick up B naught or B as the output for the mux? If S is 1. Why? Yeah. Because whenever S is 1, you're adding a 1 to the carrying of the first flighter. So it seems like you want to add a 1 to it. So you have to flip it as well. So that's 2's complement. So I'm going to flip it, which means you want to pick up B naught as output of the mux. And we introduced the logic circuits for the mux last time, and there is a better option for that. But before design it, let's look at the logic for the 2 to 1 mux first. It is how many inputs it has? 2 or 3? 3. So 2 inputs and 1 selection bit. So that's S, A1, A0. If this is a logic block, you have A0, A1, and here's S, here's Y. Zero, 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 1, 0, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1. And when S is 0, it selects A0. So whatever A0 is, just directly being copied to Y. And when S is 1, it selects A1, so just copy here. Okay, so that's a truth table K-map of the mux. What is this? Truth table. I need a K-map to design the circuit. Zero zero one 001 011 110 111. So y equals to S naught A0 plus S A1. And you can design the circuit as A1, A0, A1, and S naught. So S naught, S naught A0 or S A1. So that's why it has a lot of gates over here. That's a conventional logic gates, logic circuits for the 2-to-1 mux. And this is not even the best case because it has a static 1 hazard. So you want to group this two as well, which is going to add a extra term in this logic expression, which is A1, A0. So you need another gate to make it work properly. That's why. So OR these two together and then OR these two outputs again to get Y. Right? A lot of gates. You can see 2 gates here. How many gates here? 6. 6, 6, 6, 6. That's a lot. So I'm going to introduce a better version of the mux and do the same job, but way smaller, way more compact than this one. So see how many? 30, 32. 2-to-1 mux has 32 gates or 32 transistors in there. Done. What is this? It's called transmission gate. This is called a transmission gate or TG. Oh, transmission. It is a PMOS on the top and NMOS at the bottom, and I short it like this. So only 4 transistors, including an inverter here. You want to invert as. So still like 4 plus 2, right? Only 6 in total. And if you want to draw it in the traditional way, you can form a transmission gate like this. So that's the input, that's the output. But I normally just simplify it. I would just draw like this. Okay, a PMOS on the top. Because this is a gain and source being shorted together. So that's the NMOS, that's the PMOS. So I just want to pass the signal from A to B. So if I have the signal S here turning on, if this is on, if this is high, right? So here's high, here's low, which is on, which is off. Which transmission gate is on, which transmission gate is off. What is the signal here? If this is high, this is high. You give a high, logic high to the PMOS, it's going to be off. And this is low, I give a low, logic low to the NMOS, this is off. So it cannot pass through this TG. So here is on, because the PMOS is on, the NMOS is also on. The PMOS can transmit logic high properly, and NMOS can transmit logic low properly. But now I have a logic high, doesn't matter because I have both NMOS and PMOS inside the TG. So the PMOS is going to work over here to pull this signal up to high. So it's like a switch. You turn it on, this transmission gate is going to transfer this one to the right hand side. You just want to invert these two signals. When you're turning on this guy, you want to turn on this guy. So these two signals should be inverted. That's why it's being inverted. You got a high here, it has to be low here. That's a transmission gate. Can be used at the MUX. You can see here this circuit is doing the same job as a MUX circuit over here. Right? When S is high, it's passing B to Y. When S is low, it's passing A to Y. So you can put everything into a symbol. And here's S, and just invert it. So that's S bar or SI sometimes. You can see it's SI. So it's just inverted S. So you can create a symbol like this for this transmission gate. I'm going to ask you to use this circuit to form a subtractor in your homework 4, I guess. Oh, 3, sorry. Now let's look at the high-speed adder. So because we are designing this part, right, so this subtractor right now, and we know how to design the compact MUX already, we're going to use the transmission gate to form this guy. The full adder is still huge. So we have XOR gates, we have all the other things in there. We know how to convert a AOI logic into a complex CMOS logic gates. Right? We can directly find out the logic expression and figure out the simplified version instead of just using logic gates. Right? We can optimize the circuit structure. So we know this, and now let's design this one. So the overall subtractor, adder subtractor will be way more compact than the traditional one. This is called a high-speed adder or high-speed full adder. So I'm going to write down the conclusion first, and now let's find a way to prove it, because this is an empirical conclusion. It's hard to tell why it's just working properly, and we just need to know how to prove it. So S, the final logic expression for S is A plus A or B or CI and CO naught or ABCI. And the CO C out naught is A naught or B naught, A naught and B naught or CI naught. So that's what we're going to use to form the complex logic gates for the AOI logic. How can we get here? Since we know if we just draw the truth table for the ladder, what is S? What is CO? Traditionally, what are the old logic expressions we used? What is S? What is CO? This is what you can get from the truth table. We have done this a lot of times in 241 and somewhere else. So let's find out this first. This looks like easier. Just invert it and use De Morgan's law. We can prove it. Since we know CO is this, so CO naught is definitely this, A or B, CI or AB, not. And split the bar, change the sign. We're getting this. And do it again for this part. And then combine them. This and this is still this. A not, B not. Oh, am I going to do that? No, I'm not going to do that. So just stop here. So that's C out not. And what about S? So S is A XOR B XOR CI, which is A not B or A B not XOR CI, which is A not B, A B not CI, or A not B, A B not CI not, which is nothing can be more boring than this. Does a math teacher do all these derivations in the class all the time? For the entire freshman year from Calc 1 to Calc 3? Do I have Calc 4? No? Which is Calc 4? Something like that. I'm glad I'm not a math teacher. Have I ever slept in math classes? No? Yes? Have I been awake in the math classes? Okay, yeah. Need a lot of coffee. All right. A or B, not. Split the bar, change the sign. Zero AB or A not B not B not B is 0. Why I want to do this? Because if you look at no, I'm not done yet, because this is S. It can get here from S. And the reason I wanted this logic expression is because if I use this and CO naught or ABCI, it's exactly this. So let's do the final step to verify it. And we already know CO naught is this guy. So S equals to A or B or CI and CO naught, which we just got a minute ago, which is so this part is exactly this part. So or ABCI or ABCI. Okay. So now let's verify what is this. I'm gonna AND these two guys first. That's what I did. Because this is 0 and this is AB naught. Or A naught B or A naught CI or B naught CI. Expanded 0. Not changing, right? So it's still A naught B. This is A naught BCI 0 again. AB naught CI naught A naught BCI naught 0 0. I think I'm missing anything. What is that? So now compare these two guys. ABCI is here. A naught B naught CI. I think I'm missing a CI here by some reason. Shouldn't do this actually. A naught BCI, A B naught CI naught. This is here. It's very close. Something is wrong here. I'm going to verify this later. Don't want to take all the time in the class to do this. Just write down the conclusion, which is this. Let's find out the circuit from this logic expression. So where do I want to start with? Because I don't have a bar on the top. In that case, you have to invert it eventually, right? Let's do this first. So A or B or CI, that's the OR logic. So for the PMOS, the PMOS should be in series on top. A, B, CI so they are being connected using the AND logic. So the PMOS should be in parallel on the top. Let's do this first. What are these three? A, B, CI in parallel. You want to close it. And now this part, ABCI in series is one line, and in parallel with this guy, and in series with this part. So you want to just draw it below it. So this one is this one. CO naught. It's a PMOS. Now let's do the NMOS. ABCI in series. And this is unlogic. So this part and this part should be in series over here for the PMOS, for the NMOSes. And these OR logic should be implemented by parallel NMOSes. So you should have a CO naught here, and then 3 parallel NMOSes. Doesn't matter which is which, just A, B, C, I. So this is S naught. So you want to invert it to get S. That's how to design a circuit from the logic. What about C naught? CO naught. Since you need CO naught as a signal for the S logic, and also you need a CO for the final result. So how do you want to proceed? With this guy. Yeah, of course. First, A naught, B naught will be in parallel and series for the PMOSes. In series, right? Am I using this one? You have two options here. You can use this, or you can use either way. Okay. So what I used here is this one actually. This is just for this part. This is easier than this. So let's use this one. A or B should be in series, and AB should be in parallel. A, B in series, and CI is unlogic, so in parallel. For AB in series, and ABCI. So CI should be in series with the parallel AB. That's B. Let's find out the stick diagram for these two circuits. Let's look at the first one. How many transistors? 1, 2, 3, 4, 5, 6, 7. So I need 8 P pluses. 2, 3, 4, 5, 6, 7, 8. So 3 transistors in parallel first. And what I did over here is I introduced VDD to these two nodes. So I'm getting 1, 2, 3. So in that case, I have to short these two guys to make the 3 transistors in parallel, right? So this node is here, and then 3 PMOSes in series. How to do that? So three more PMOSes in series and in parallel with 1 PMOS. So you got 4 PMOSes here. How do you want to plan on this? Because we know this node is this node. So if I connect this wire to here, it's going to directly flow through 1, 2, 3 PMOSes. Will that work? Would this work? How? So this part is this part, and here's a node. And this node is actually being split into 2 branches. One goes to here, one goes to here. And one goes to here, it runs through 3 series PMOSes directly. 3 PMOSes directly. The other one just runs through 1 PMOS, which is exactly this part. So it's going to be merged as this node, as the output, which is this node. All right, now let's look at the NMOS. Here is the output from the PMOSes. And I need 2 branches. One has 3 NMOSes in series. So I can directly short it to here. 1, 2, 3. Ground. So this part is this part. So that is done. And now I need 1 transistor and 3 transistors in parallel by doing anything from here. So I connected these two together and I grounded this part. See if this works and how this works. Because I want to, so this part, I want to do this, implement this logic. So I need to run through a NMOS first. So go through this NMOS first, and then 3 NMOSes in parallel. Right? 1, 2, 3. So I want to short this to ground as well. So this part is 3 NMOSes in parallel, and this part is this little NMOS here. That's how design this part. And that is S0. And to invert it, just directly add a inverter after it. So here's S. All right. And let's look at this part. Since we directly find out this circuit from this logic expression, so the output here should be CO0. And we need to invert it to make a CO out of it. Since we have CO0 already created by this circuit, so we can directly use that CO0 signal for the S. It's part of S. So we can directly short it to here. It's just in one layout. Now let's see how we can design the stick diagram from this part, from this guy. I didn't try to find out one string to implement it, but you know, I can design a circuit out of it, but it's being split by ones in the middle. If you can find a way to just design everything in one string, which is great. So what I did is, you know, on the top, I have 3 and 4, so totally, so 3, actually 2 and 3, so 5. So I'm going to do this 2 first, and I'm going to do this 3 after it. This makes things way easier if you split it in the middle. So what is this? This is these two PMOSes in parallel. So what I'm going to do is I will just short it here and then connect these two. So that's 2 PMOSes in parallel. And after that, I need 1 PMOS in parallel with 2 series PMOSes. So I can directly short it here. So this is the 1 PMOS. That's the output. And I want to parallel these 2 PMOSes from here. Series, actually. These 2 PMOSes are in series. So directly run it through it and then merge as this node. Okay. So introduce that wire, introduce that signal to here, and then 1 branch, 2 branch. So the first branch runs through this single PMOS, and the other branch runs through 2 PMOSes in series. So you can merge the signal out here. That's the output. Then the NMOSes, first, you got 2 NMOSes in series, and then the same signal, but you have 1 and then 2 in parallel, 1 in series. That's pretty simple. It's pretty much the same structure as here, right? So I just want to directly connect to here. Then it's 1 in series and then 2 in parallel. Right. 1 in series and 2 in parallel. So the output from this stick diagram is CO0, and you want to invert it. Just add an inverter out after it. So here is CO. This combines these two layouts so you can get a compact version of the slider. That's going to use, and then you just put everything into a box symbol so you can use it for this circuit. You can form a 3-bit subtractor, or if you just add more, it's going to be an 8-bit slider, which are going to be used in the lab tomorrow, I guess. All right. We're done for stick diagrams. Now we're going to move forward to run the C5 layers. It's going to take a week to cover all this stuff. So you can find all these materials being covered here in Dr. Baker's CMOS textbook. It's exactly the same stuff being covered in the textbook. First, let's look at the N-well. Since we know that we can dope a N+ material directly to the P substrate, it's called N-well. And it actually forms a pin junction. And we know that whenever you got a pin junction, there will be a depletion region being formed. Because of what? Depletion region. The pin junction, right? It's not desired, but it's there. So there will be a depletion region like this. Okay? And remember, for the diode, whenever you have a depletion region, if you forward bias the pin junction, is the capacitance of this region, there will be a parasitic capacitor. Is the capacitance here getting smaller or bigger if you forward bias it? Increase, why? So C equals to what? Epsilon D over A? No. A over D? A times D? A to the power of D? Which one? N is larger, we get more space to hold the charges, right? So A should be on the top. And whenever it's getting longer distance in the middle, the capability of holding the charge will be decreased. So whenever you forward bias that pin junction, it's compressing the depletion region to make it thinner. So whenever it's thin enough, the charges can run through it. So you can get the pin junction get conductive, become conductive. So which means when D is increasing, C will decrease. Okay, but whatever, there will be a parasitic capacitor here everywhere. And also we are making an N-well as a resistor, so there are a lot of resistors in between as well. So you can model the P sub is being grounded, so you can model the distributed resistors and capacitors in this way. You think you just laid out a N-well resistor, but actually it's not. It's something like this. Why? Because the depletion region has capacitance in there, parasitic capacitance in there. or parasitics. You know, so you can see this term in some of the textbooks. Parasitic capacitors. Why do we want to model this in this way? Model the unwound resistor in this way. Because this causes time delay, so we have to take this in consideration. And the way you want to model this is because the unwound resistor is being counted as how many squares. Because if we know here's the depth of the unwound resistor, and we know the resistance equals to rho times L over A. A is a cross-sectional area. And in one of the homework questions, I think probably 20% of the guys didn't give me a correct answer for that. So why the sheet resistance is constant, right? Because A is the width times the depth, and the depth is a constant. So it is actually equals to rho over D times L over W. And if we only consider about the squares, because if you times two of this, they can be cancelled. So we can use the square as a sheet resistance for the unwound resistor. So it's easier to calculate the resistance. So these can be modeled as R squares. No matter what's the shape of the unwound, right? Can be like this, can be some kind of different shapes. You just use the width as the unit length and make into different numbers of squares. So every resistor represent one R square. And also we can find out the capacitance as well. I'm going to introduce how to find out the capacitance after it. And we can calculate what's the time delay from here to here. So there is an equation or an easier way to calculate it. If you just look at all these RC circuits, it can be complicated to calculate the final time delay from V in to V out. But actually, there's an easier way to do it. I'm going to introduce that method on Wednesday. Okay. All right, that's everything for today. See you tomorrow.